Hello, ladies and gentlemen. My name is Christian Jimenez, and this is my Lab 4. The purpose of this lab was to analyze the motion of a spring, mass, and Earth system, both oscillating as a spring and pendulum, to prove the energy principle. Some fundamental physics principles and corresponding visuals are Hooke's law is force of the spring equals the opposite direction of the stretch length of the spring times the stiffness of the spring times the direction of the spring stretching. And then the spring potential energy is just the integral of that Hooke's law, and that ends up equaling 1/2 kx squared. And the kinetic energy formula is the kinetic energy equals 1/2 mv squared, which looks similar to the formula above, but represents something very different. And a quick note on gravitational potential energy on a pendulum that sometimes trips me up is that gravitational potential energy, like always, is only based on vertical height. And so if you have a pendulum that's on the lower part of its swing, it goes along displacement but doesn't actually move much in the vertical direction. So it's important to make sure that in any calculations that you do with like a pendulum with gravitational potential energy that you're only using vertical height. And the energy principle states that the change in energy of a system equals the work done by the surroundings plus the loss in thermal energy. And in this case, there was no force from the surroundings, no work done, and also the thermal energy loss to the surroundings is negligible. We can assume that the change in energy in this case is zero. And Newton's second law, as always, is force net equals change in momentum over change in time. System and surroundings. The system is the earth, mass, and spring. The surroundings is everything else, and potentially relevant, which I'll explain later, is the air. All right, here's my tracker video. I ended up moving that pink axis thing because I was having some trouble with the code, but the general idea is we All right, initial conditions, that's the mass, that's the stretch length, that's the initial position, that's the initial velocity. It's a zeros on everything because it starts from rest. And this is a period I found by averaging the distance between three of the peaks on the y, and that's what I got for that. And solving for k, I got that the period is equal to 2 pi times square root of mass over k, and I rearranged the equation to calculate the k value, as you can see down here. And solving for the initial relaxed length, I took the net force on the system for all directions, and I got the Hooke's law minus force of gravity to solve for the relaxed length of the spring. And here's my code. I made a note to myself to remember to explain it very well. Here are just the initial conditions that from earlier that we were putting, more initial conditions, and this is the total length of the spring, and we got that to be the position of the mass minus the position of the start of the spring, which makes sense. And then the direction of this length is just that length divided by its magnitude. And then the stretch length of the spring is the total length minus the relaxed length, which is up here. And then over here are where some of the energies that we described earlier in the principles. And then we set the forces here and use the velocity update formula and, using the net force that we set up here. And then the position update formula, which is self-explanatory. And yeah. And then here is the model of my code running. Okay. And here are the graphs of my model versus experimental. As you can see in the x direction, the model and experimental actually look pretty similar besides a slight horizontal shift. But in the y direction, there's a slight horizontal shift, and the experimental peaks are just a little bit lower than the peaks for the model. And some possible explanations for this. For the horizontal shift, it can be that the man in the video let go of the mass a little short of the full spring stretch length. So that would make it so rather than going fully up and down straight from the beginning, going fully from its max length down and its max length up. It starts part of the way up, then continues going up, then goes down to the max length down, and thus might have started the experimental a little bit earlier than the model. And then for the reason for the lower peaks in the experimental is maybe there was also some motion in the z direction that may have caused less oscillation in the y direction, and thus made the peaks lower than was expected because we set all z equal to 0. And the energy principle satisfied? Short answer is yes. No thermal energy is lost, nor work is done to the system. Delta E is 0. Well, maybe there is some thermal energy lost due to the air surroundings and air resistance, but this is negligible. So the model gets that delta E is 0. And energy is converted within the system very much, as you can see, with these different means, such as like the spring potential energy, kinetic energy, and gravitational potential energy, but it's not lost. In comparison of oscillation periods, I set the first equation is x. The second is the y. Or wait, no, it's the other way around. Oops. So first one is y, second one is x. As you can see, they're different. And the interpretation of this is just like a diagonal velocity. Each individual dimension will have separate, distinct components. The same is true with spring/pendulum oscillation periods, and thus the stiffness or resistance of stretch, the spring and x versus y will be different. Some sources of error or losses of energy due to surroundings or resistance, though this is negligible, or just use your error in track replacement. All right, thanks for watching. See you next time.